Welcome back to the channel. Watch the video until the end, leave a like, and subscribe to the channel to support us. The Hubble constant is one of the most important quantities in astrophysics. Its value tells us how fast the universe is expanding and, among other things, allows us to estimate the age of the universe. Astronomers have been trying for nearly a century to determine its exact value, and despite making huge strides compared to the past, there still exists disagreement over what the accurate value of the Hubble constant is. In recent years, a discrepancy in the values of the Hubble constant measured using different methods has emerged. This discrepancy has also been dubbed the Hubble tension, and the true reason for the disagreement is not yet known. Is it just an uncertainty in the measurements, or is there something more profound? Let's try to understand it. First, let's briefly recall what the Hubble constant is. At the beginning of the 20th century in the 1920s, Edwin Hubble, the American astronomer, made two rather important discoveries. The first is that there are other galaxies beyond our Milky Way. The second is that these galaxies are moving away from us at a speed proportional to their distance. This law, which links the speed of the galaxies moving away with the distance from us, is called the Hubble law, and the constant of proportionality, which indicates, given the distance, what the speed of a galaxy is the Hubble constant. It is important to underline that it's not that galaxies are specifically moving away from us, but the universe itself is expanding, and so any pair of distant points in the universe is separating at a speed that grows proportionally to their distance. If you take any pair of very distant galaxies in the universe, they all follow exactly this law. The value of the Hubble constant is measured in kilometers per second per megaparsec. The megaparsec is a unit of measurement for very large astronomical distances. 1 parsec is about 3.26 light-years, so a megaparsec is equivalent to 1,000,000 parsecs, or about 326 million light-years. The fact that the Hubble constant is measured in kilometers per second per megaparsec means that two objects separated by a distance of 1 megaparsec are moving away from each other at a certain speed expressed in kilometers per second. The first measurement of the Hubble constant, made by Hubble himself along with his collaborator Milton Humason, gave a value of the Hubble constant of about 500 kilometers per second per megaparsec, which meant that two objects, for example two galaxies, separated by a distance of 1 megaparsec should be moving away from each other at a speed of 500 km/s. This initial value led to an estimate of the age of the universe of about 2 billion years, a value incompatible with the estimated age of the Earth, which was already known to be much older. This immediately raised a problem, as the universe could not be younger than the Earth. The explanation was that Hubble's early measurements were very uncertain, so the value of 500 km per megaparsec was wrong. Over time, the error was corrected, and more reasonable values of the Hubble constant were found. For much of the 20th century, there was great difficulty in understanding what the exact value of the Hubble constant was, with significant disagreement among different groups of astronomers over what this value was. Still, up until the 1980s, there were large differences in values found by different groups. For example, the great American astronomer Alan Sandage found values of the constant of about 50 km per second per megaparsec, while the French astronomer Gérard de Vaucouleurs found values of about 100 km per second per megaparsec. The situation seemed to be definitively resolved in the 1990s when, with the launch of the Hubble Space Telescope, one of its main goals was precisely the exact measurement of the Hubble constant. A value around 70 km per second per megaparsec was found, which seemed to be finally correct. However, as mentioned, in recent years the situation has been complicated by the discrepancy in the values of the Hubble constant, measured using different methods. Some methods based on direct observations, such as those using Cepheids as standard candles or type Ia supernovae, tend to provide values higher than 70 km per megaparsec, while indirect methods, based on observations of the cosmic microwave background and Big Bang models, tend to provide lower values. This discrepancy, known as the Hubble tension, is at the center of a lively scientific debate. It could indicate simply that there are underestimated uncertainties in the measurements, or it could suggest the need for new physical models that go beyond the standard model of cosmology. It is important to emphasize that measuring the Hubble constant is not simple. The velocity of galaxies moving away, measured through the redshift, is relatively easier to calculate compared to the distance of these objects, whose measurement is complex and subject to greater uncertainties. Over time, astronomers have developed and refined methods based on distance indicators, such as Cepheids and Type Ia supernovae, to measure astronomical distances with greater precision. In recent years, new techniques for measuring the Hubble constant have also been developed, such as the use of gravitational waves and gravitational lensing, which offer new perspectives and potentially can help resolve the Hubble tension. Despite the current tension, progress in the precision of measurements of the Hubble constant is a significant scientific success. This precision could indeed be the key to discovering new physical phenomena, or to confirming the need to revise current cosmological models. Science proceeds through a continuous process of inquiry, experimentation, and revision of models based on data. Therefore, we will continue to collect and analyze data, hoping to resolve this intriguing discrepancy and to better understand the universe in which we live.